Okay, so welcome back. We're going to talk about the relationship between work, delta G, and cell potential. And this is probably my fourth or fifth time trying to make this video because I keep forgetting to put a negative sign into one of my answers. So if you happen to see that, just remember the answer should have been negative. But I'm pretty sure this is going to be the last time I make this video, so I hope it works out. Here we go. So, work, max, and delta G are interchangeable. They mean essentially the same thing. Both of these equations are more or less the same. The only difference is that we have delta G written here, work max written here. But other than that, there's no difference because charge and N times F are the same thing. So Q is charge, N is moles of electrons, F is the Faraday constant, which is 96,485 coulombs per mole. So charge is moles of electrons times coulombs per mole times the Faraday constant. Emax is just exactly what we're used to calculating using the reduction table, or a reduction table. And so, really, these two equations are the same. This is going to be the more common version of the equation as we use it. So a couple things to keep in mind. Galvanic cells operate real processes, so their work is never going to be maxed out. So what we calculate with these equations isn't going to be what actually happens. It's going to be what could or should happen. To measure the efficiency of the cell, in other words, to figure out how close to maxing out the work it comes, we're going to divide the actual work that gets done by the work max that we predict through the use of these equations, and we can multiply times 100%. Now, if we're setting up a proper galvanic cell, the potential is going to be negative. Positive, rather. The potential is going to be positive, and so as a result, we would expect that the cell is going to be able to do work. And because the system, the cell, the system being the same, is doing the work, the result should be negative. And again, I've been messing that up with the calculation that I've been doing, and so look for that when I report my answer this time. So with all those things being considered, don't forget that Faraday constant is 96,485 coulombs per mole. And so, yeah, I think we can go ahead and get started with an example problem. And so, as we're doing this, we're going to be taking a look at standard cell potential. And if it's positive, then the process is going to be spontaneous. And if it's negative, then the process will not be spontaneous. And that's going to be our clue for answering this question. Is the reaction spontaneous? But as we work this, we're simultaneously going to be able to figure out the moles of electrons. And I'll show you how that's going to work out right now. So we have our balanced equation. That's been established for us. And so at this point, we already know what direction this equation should be set up as. And this particular cell potential is 0.80 volts. Now normally, the calcium solid equation half reaction written as here, normally this is negative 2.87, but because it's written in this direction, not as reduction but as oxidation, the cell potential value is actually flipped and it becomes a positive 2.87 volts, giving us a positive 3.67 volts. So what that means is that the reaction is spontaneous. Unfortunately, if we were to add these two half reactions, we would not end up with the resulting balanced equation because the electrons are not yet balanced out. We have to have a match for the number of electrons that we give up as we take in, which means that I need to double all my values through this half reaction. And now that I've done that, two things you need to remember. First of all, changing the coefficients for this half reaction has no effect on the standard cell potential for the half reaction. But the other piece is that this coefficient here associated with the number of electrons is the value for n, which means that now when it comes time to answer the question, what is the maximum work that can be done with a cell based on the following reaction, I'm now in an excellent position to go with delta G is equal to negative n times F times the max cell potential. And now I've got all the values that I need because I calculated the max cell potential, I know the value of n is 2, and the Faraday constant's a constant, so that's very easy for us. And so delta G is going to equal negative 2 times 96,485 times 3.67. And so as a result, delta G is going to equal negative 708,200 joules. So a couple things. I did do a little bit of rounding there in order to get my numerical result. But another thing is, when you're calculating delta G based on standard cell potential, your unit is going to be in joules. And so if you need to, for example, if they were asking for a kilojoule answer, you're just going to have to make that adjustment on your own. But that's pretty much how you're going to calculate for work max, right? Because maximum work is free energy. And so the two equations work together. Alright, so we could almost go back and say work max is equal to delta G is equal to negative n times F times cell potential max. So with that in mind, we've got this example problem here, not quite related to what we were just talking about, but still something worth. Will silver form or dissolve in nitric acid? And we've been given the half reaction for the nitric acid. And we know that the process is going to work spontaneously in a direction that gives a positive standard cell potential. So we've got one half reaction, and the question is involving silver. We know the half reaction for silver looks like this and has a standard cell potential of 0.80 volts. If this half reaction remains as is, then silver will not dissolve, because the result of this half reaction working is a solid, not an ion. But at this point, we have to go ahead and take a look at our cell potentials, because with both of these being reduction half reactions, one of them is going to have to flip. And we're going to need to pick the equation to flip that will give us a result for the total of a positive cell potential. With the cell potential for the nitrate half reaction being more positive than that for silver, silver is going to have to be our selection for what flips. And so what's going to end up happening is solid silver, through the course of the addition to the nitric acid, is going to turn into silver ion. The resulting cell potential is going to become negative, which means that rather than not dissolving, the silver is in fact going to dissolve. And so it's these two half reactions here and here that we're going to be utilizing, and the result ends up being, for the process, a cell potential that is equal to positive 0.16 volts. So that's pretty much what I have on this subject. I think this was the best outcome for me in terms of this video yet. We'll see how it works out in the editing room. But hope this helped you guys out, and good luck putting it to use for yourselves.